So hello everyone. I'm not even sure why I'm sharing because these classes take like 8 hours to upload, and I don't have the time to do that. But maybe my computer will be fixed, and I'll eventually get them up there. So we are now in. Yeah, someone said something about YouTube. I have to think about that one. I want to see if I don't know if I want to be out there on YouTube. But we'll see. Someone said something. Where are we? So we are in week 8. That would put this at class number 14 because we missed one for the quiz. So this is our 14th lecture, and we are talking about hypothesis testing. And we are going to continue with hypothesis testing in the context of some examples. Okay, so we're going to go with check our skills. And I'm going to do some of these. So let's start with number 19. I would like you to read number 19 at first. And then after a minute or so in chat, you have one of 4 options, either A, B, C, or I have no freaking clue what they're even asking for. It's okay, Martin, welcome. Number 19. You use software to carry out a test of significance. The program tells you the p-value. And of course, if we haven't done any of this stuff, if we have never covered p-values, just say, hey, we never learned that. So I'm more than happy to explain. But I think we did. So the program tells you that the p-value is p equals 0.011. Hi, Ani, good to see you. You conclude that the probability computed, assuming that H naught is blank, of the test statistic taking a value as extreme as or blank extreme than that actually observed is 0.011. I will explain in a second. Yeah, I want to see if anyone knows the answer to this question before I explain it. So, and I don't know the perfectly acceptable answer. I'm totally okay with I don't knows. I would love if there's any correct answers here between A, B, C, or I don't know. So I have a B. I have a few I don't knows. I even have an I don't know, which is, I guess, more extreme than an I don't know. I have a lot of I don't knows. We did do p-values, correct? Is this a term that sounds familiar? You did, right? I thought we did. Okay. You might not remember it, which is fine, but does anyone know the answer? I have one person who said B. I have a lot of I don't knows. I'm not sure what I'm waiting for. I should be either getting A, B, C's, or I don't knows, but I'm getting a lot of nothing. I can't do much with nothing. I can do a lot with I don't knows, and I can do a lot with A, B's, or C's, but I can't do a lot with nothings. So if you don't know, just say I don't know. It's totally okay. I have a C. I have a B. I have no clue. That's an IHNC, not just an I don't know. I have no clue. It's a whole other level. Probably past I don't know. No. So let's talk about this one because no one seems to know. Which just says that I have no idea what I'm doing as an instructor, which is fine. I've been there before. I'm just kidding. I'm pretty good. But this stuff is hard. And it's been a long weekend. And you haven't done a lot of homework on it because I put the homework up only a couple days ago. So it's totally okay to not have remembered. Totally understandable. Let's get to it. We are dealing with a situation where we assume that we have a normal distribution. It's one of the basic assumptions of the whole hypothesis testing. If it's not normal, can't do much. And we always are assuming that H naught, the null hypothesis, is true. Everything we do in a hypothesis test, without exception, is under the hypothesis that the null hypothesis is true, or under the assumption the null hypothesis is true. The null hypothesis is going to claim that the mean is some specific value. The null hypothesis says that the mean is some specific value, usually labeled as mu naught. Mu naught could be 0, it could be 5, it could be -3, I don't know. But the null hypothesis is that the mean is a specific value. And we work under the assumption that the null hypothesis is true. The alternative to that is one of three possibilities. Either the mean is greater than what you say it is in the null hypothesis, or the mean is less than what you say it is in the null hypothesis. And what's the third possibility?
Not equal to.
Or the mean is just straight up not equal to. We call this a two-sided hypothesis test because we're okay with it being not on the greater than or less than. Now, when I do a hypothesis test, you will get a value, your sample mean, X bar. Your sample mean is your value that you get from your sample. Now, chances are that your sample mean is not going to be equal to the actual mean or what you think the actual mean is, but it will be some other value. Does that make sense so far? The p-value is the probability of getting what you got or something even further away from the mean. Something even further away from the assumed value. If it's a one-sided test, it's just the probability of being in there. If it's a two-sided test, then there's another way that I can be further away from the center value than my actual value. Besides landing in here, where else could I land to be further away from here than what I actually got?
Is it on the other side of the tail?
It would be exactly. If it's two-sided, then if I go to the other side, it's also being in the symmetric, diametrically opposed area. So either way, I don't know in this particular problem whether it's a one-sided test or a two-sided test. Doesn't really make a difference. They give me the p-value. The p-value is nothing more than the value, the probability, under the assumption that the null hypothesis is true, of getting what you got or something even more extreme. So taking a value as extreme or more extreme than the, not less extreme, but more extreme than the actual observed value. So therefore the answer is A. Does that make sense? So let's do number 20. I will give you a, okay, we're reviewing these terms like p-value, and this one has these terms statistically significant. I don't even remember if we specifically did statistical significance. So let me explain before this question what statistical significance is. And I can still do it in the context of this problem. We always work under the assumption that the null hypothesis is true. So if I tell you that the null hypothesis says that mu is equal to some value, if I end up somewhere far away from that value, is that a likely occurrence under the assumption of the null hypothesis validity? If the null hypothesis were really true, Would I end up somewhere over here? Highly unlikely, correct? In fact, if I did end up somewhere over here, I would probably say, you know what? Chances are it's really much further to the right. All right, if I ended up somewhere over here, this is much more likely of a scenario than this one. Yes, if you end up so far away from what you expect, the p-value is really small. In other words, the likelihood of getting that, if the null hypothesis were true, is so small, I would reject the null hypothesis. That's what statistically significant means. A result is statistically significant if I would then reject the null hypothesis. If the p-value is small enough that I would reject the null hypothesis. What does small enough mean? So your alpha is your level of significance. If the p-value is less than alpha, if your p-value is less than the level of significance, then we reject the null hypothesis. Statistical significance is a result that would be unlikely if the null hypothesis were true. A statistically significant result is one that is unlikely if the null hypothesis were true. So an alpha of 0.05, someone asks, is the alpha of 0.05 the same as 95%? Not exactly, but there's a connection. A 95% confidence level would then sort of correspond to an alpha of 0.05. So there is a connection there that we'll get into later. High p-value, don't reject. Low p-value, reject. But it's not always 5%. That's not always the cutoff. If they give you a specific alpha, they're giving you a specific cutoff. So if they tell you that alpha is 0.05, okay, so alpha is not always given, but if it's not, you can assume that alpha is 0.05. Okay, 0.05 is kind of like the default alpha. But in this example, they give you multiple possibilities for alpha, and they're asking, is the result statistically significant at this, but not this, or this, is both of them, whatever. You have three possibilities. So you have a p-value. The question is, you can't hear anything at all? Well, that's not good. I'm going to tell her to relog. Or whatever the terminology is. So where was I? I lost my page. No, that wasn't it. That was it. Okay. So let's do this one. Yeah, okay. So number 20. A, B, C, or good straight up, I don't know. Can you do another example of statistical significance? Well, we'll do number 21 as well in a second. We'll do two examples. So you can get the first one wrong, but then you can't get the second one wrong. So I have an A. I have a couple A's. I have 3 A's. 3 for 3. As we say in Hebrew, that's a chazaka. Anyone here speak Hebrew? No, just me. So A and I don't know. How do you do A and I don't know? How does one do an A and then I don't know? That's not allowed. So if P is 0.011, is that less than 0.05? Therefore, it's a statistically significant result. If the p-value is less than alpha, it is statistically significant. Is it less than 0.01? Then it's not statistically significant. So the first one, part A, says that it's not statistically significant at either A or B. Is that correct? Either alpha equals 0.05 or alpha equals 0.01. Is that correct? Based upon what we just said? La la la. No. What about statistically significant at 0.05, but not at 0.01? Well, there's your answer. Alpha is the level of significance. It's essentially the cutoff points at which you decide whether or not you are going to reject or not reject the null hypothesis. If the p-value is less than alpha, you reject the null hypothesis. If the p-value is not less than alpha, then you do not reject the null hypothesis. Statistically significant essentially means the p-value is less than alpha. So if the p-value is 0.011, it is less than 0.05, statistically significant, but it is not less than 0.01, not statistically significant. Let's now try number 21. How do I clear this? Oh, okay. So if p-value is less than aloha, you reject. Well, aloha is Hawaiian for hello, I believe. I don't really see how that is relevant to this problem. But if you meant alpha, then yes. If the p-value is less than alpha, you reject the null hypothesis. So I knew what you meant. So I was just trying to be funny. I'm not sure if I succeeded, but you LOL'd, so maybe I was. Who knows? All right, so let's try number 21. 21 actually requires a calculation, so don't try to do this in your head. I don't know. You can't just go directly to I don't know without actually trying. Well, maybe you did try. I don't know. Did you try? I hope you tried. Trying is good. We'll see if anyone else can figure it out. Anyone think they have the answer? Someone says B with a question mark. B? A? These are very hesitant answers. B. Definitive, decisive, demonstrative, I believe is how you pronounce it. Demonstrative. Not demonstrative, but demonstrative. It's a good word, demonstrative. I like it. Anyone else? I don't know. I love it. I don't know is a fantastic answer. B, I think. B. I don't know. I'm not sure. I don't know either. So I do have some definitive B's and some question marks. Oh, Ani, I'm sorry. I was trying to figure it out, but I don't know. I don't know. Let's see if I can figure it out. I have no idea. Let's see if I can figure it out. So we know, oh, she's crying. Don't cry. Don't cry. I don't know how I can do one of those things. I don't think I can do one of sharing. Too bad. Okay. So we have a Z. We have a normal distribution. And we know that the center of every standard normal distribution is 0. And my value is 2.29, which is over here somewhere. That's my value, 2.29. And the question is whether or not it's statistically significant or not statistically significant at different values. In other words, I got to calculate the p-value. Because the only way you can determine whether something is statistically significant is to compare the p-value to aloha. If the p-value is less than or equal to aloha, you reject the null hypothesis. Otherwise, you do not reject the null hypothesis. So how do I find the p-value? Well, what is the p-value? It's the probability of getting what you got, which is this value, or something even more extreme, which is anything out here. Is it also the stuff on the other side? Not for a one-sided test. If it was two-sided, then yes, I would have to look at the other side as well. But this is a one-sided test, so I only look at the one side. So how do I calculate the p-value? How do I calculate the probability of being past 2.29? How would I do that? Hopefully you all haven't forgotten all the stuff from previous chapters, because p-value calculator on Google. I love it. The p-value calculator on Google. Let's do that. So let's load up the p-value p-value calculator on Google. It's a great idea. And we're looking, no crunch it please on board. We're looking at the p-value from a z-score. 2.29, and they even ask us to check the significance level. So one-tailed, enter my z-score, and then press the button. So the p-value is 0.011011. They tell me the result is significant because p, my p-value, is less than alpha, my significant value. Two-tailed means that it can be, that I'm not only looking at greater than or less than, but I'm looking at not equal to, which means I don't mind if it's greater than or if it's less than. Either one works. But this is a one-sided one. So we go back because my p-value is 0.011011. So now that I know that my p-value is 0.011011, I will write that just to have it for posterity's sake. P-value equals 0.011. So go ahead and answer A, B, or C. How do you find the P without a calculator? You don't. You do not find the P without a calculator. You use a statistical program, use Google, use a calculator. You do not do it without a calculator. There's no way. Oh, you could use a table, but you don't do it by hand. There's no computation that you can make that would do it. So let's see, statistically significance. Well, it's less than this alpha, but it's not less than this alpha. It's less than this alpha, but it's not less than this alpha. So the answer should be B. And the answer is B. Statistically significant at alpha equals 0.05, but not at 0.01. What a great question. Lesson number 17.22, because I think 17.22 is something that I might not have talked about. So go ahead and read 17.22. If it's two-sided, would it be statistically significant at 0.1 as well? You mean 0.01 first of all? So here's what you do for two-sided. It's a one simple fix. Well, first of all, yeah. So let me just answer that question. It's a great question. If it's one-sided and you have this value here, the p-value is some number, which is the probability of being past what you got. If it's two-sided and this is what you got, then the p-value corresponds to not just this area, but also this area. So how does this p-value relate to the original p-value? What's the mathematical relationship to whatever this number is compared to whatever this number is here? Anyone know? Let's be more concrete. Suppose the p-value here is equal to 0.03 as an example. What's the p-value here if the p-value in the first case is 0.03? Remember what the p-value is. It's a probability. It's a likelihood of getting what you got or something even more extreme. Here, more extreme is here. Here, more extreme is here or here because it's two-sided. So if the probability was 0.03 to land in the shaded region here, what's the likelihood of landing in the shaded region in this case? 0.06, it just doubles. The only difference between a one-sided test and a two-sided test is the p-value for the two-sided test is twice the p-value for the one-sided test. So remember, we're always checking whether the p-value is, it's the same alpha. Alpha is just the level of significance. That doesn't change. The only thing that changes is your p-value doubles, which means since you're rejecting the null hypothesis, if the p-value is less than alpha, this p-value is bigger, which means you're not going to reject as much because it's harder to be less than alpha when you're a bigger number. So you could be statistically significant here, but not necessarily statistically significant here. But if this is statistically significant, then this is also automatically statistically significant, because if this number is less than alpha, then certainly this number is less than alpha. Does that make sense? Okay, good talk. So let's now do number 22. It says the gas mileage for a particular model SUV varies, but is known to have a standard deviation of sigma equals 1.0. It's normally distributed. And we have 3 test results of 19.3, 19.9, and 19.8. We want to test whether or not mu is equal to 20 miles. And the question is, what is your Z statistic? Google, yes, Google does everything for us. That's correct, but it's nice to know how to get it. So Z is nothing more than your value that you got minus the assumed mean divided by your sample standard deviation. And this is nothing more than the Z-score formula from chapters and chapters and chapters ago. So what is our X bar? Our X bar is our sample average. That's the average of 19.3, 19.9, and 19.8. How do I find the average of 19.3, 19.9, and 19.8? What's the easiest way of getting that? Anyone?
Add them up and then divide by 3, and then you get 19.7.
Okay, well, I'm going to keep all my decimals because I don't want to round to the end of the problem. I'm just going to write 19.6 bar. Minus. Now we subtract the assumed mean under the assumption of the null hypothesis. What is the assumed mean under the assumption of the null hypothesis going to be?
Is it 20?
It's straight up 20. They told me that, right? That's what we're testing. It's a null hypothesis is mu is 20. And then we divide by the original sigma over the square root of n. What is the original sigma? 1. Excellent. And what is the square root of, well, what is n in this case?
3.
3. There's 3 values. So I take my 19.6 bar and I subtract 20. And then I divide by 1 over the square root of 3. And when I do that, I get negative 0.577. Now, what I want to show you is what crunchit, the evil crunchit that's only for rich people. I want to show you that what is this 3 here? Oh, that was n. I want to show you what the evil crunchit would do in this scenario. So how do I load crunchit? Here we go, crunchit. Okay. Where's a 19.6 coming from? We just averaged these 3 numbers, 19.3, 19.9, and 19.8. That's my sample average. It's just the sum of them divided by 3. Got it. So let's go back to crunchit. So what are we doing here? We are computing we're doing a hypothesis test. So I go to Z, I go to 1 sample, and I go to hypothesis test. Now, which aspects of the hypothesis test do we have? What is the mean under the null hypothesis? Let's start there. The mean under the null hypothesis is 20. That's my assumption. Is it a one-sided? And if it is, greater than or less than, or is this a two-sided hypothesis test? Do we care about specifically less than 20, specifically greater than 20, or are we concerned with just not being equal to 20?
It's two-sided, so not being equal to 20.
I would think so as well, because it doesn't say anything that let's read the question again. Sometimes you gotta think about it. It varies. So I guess what we're testing is what's the average gas mileage, and if it's less or more, I'd be interested in knowing for marketing purposes. So it looks like it's a two-sided. What is my standard deviation? What is my sigma? 1. Am I using summarized values where they tell me how many in my sample mean, or do I actually want to do the actual values? Well, in this case, there's only 3, so let's do the actual values. What are my actual values? 19.3 was it? 19.9, and what was the third one? 19.8? Is that what they were? Yeah. And we'll call this variable 1. So we're going to use variable 1 as my sample. And I'm going to calculate. And what does it tell me that my Z statistic is? Anyone?
Negative 0.574.
Which is exactly what we had before. And what's my p-value?
0.5637.
Is that a statistically significant result or a not statistically significant result? It's not. If there's a 56% chance of something occurring, then when it occurs, you don't question the validity of the null hypothesis, right? I mean, it's going to happen more often than not. Why would you say, oh, null hypothesis isn't true? That doesn't make any sense. So you do not reject the null. I don't have to give you an alpha for that. You just do not reject the null hypothesis. Okay, does that make sense? I hope so. Let's do number 23. Go ahead and take a minute and read that. And then pick A, B, C, or the always welcome IDK. Sorry. Can we use another website next for the broke ones? Oh, I'll think about it. It's just Crunchit is so nice. So easy to use. A, B, or C? Or I don't know. C, we got a C. Someone said C. Anyone else? A, B, or C? I take it back. I think it's B. I got a B. Any A's? Any IDKs? Any IDHAFCs? So if you don't know, that's fine. Just say, I don't know. I would like to see a stream of I don't knows rather than just blank. I can't do blank. I don't know if that means I'm still working on it or what. If you don't know, you don't know. That's totally fine, but say something. Let's not use Crunchit, please. I won't use Crunchit. I don't need Crunchit for this one. There's no computations here. This is not a Crunchit problem. How do we, right, there it is. So there's always a null hypothesis, and there's always an alternative hypothesis. The sample is taken after you've set up your hypotheses. 16.5 comes from the sample. So why would the sample play any role in either the null hypothesis or the alternative hypothesis? The null and alternative hypotheses are what you're testing and what you think it might be. You don't think it might be 16.5. You take a sample and it gives you 16.5. You then use the sample to either reject or not reject the null hypothesis. The sample plays no role and should never appear in either the null hypothesis or the alternative hypotheses. So B is out. Now, what does the researcher think will happen if she makes a loud noise? She thinks that the mice will complete the maze faster. Faster than what? No, the 16.5's got nothing to do with her hypothesis. That comes later after she does a sample. She thinks it's less than 18, which means she's testing against that it's equal to what? The null hypothesis is what it would be if there was no change. She's testing whether it's equal to 18 or it went down. This is the null hypothesis. This is a no change hypothesis. This is what it's been, the hypothesis, the status quo hypothesis. This one is, could it be this instead? She thinks that it's going to go down. Does it? Let's test. Let's test what it's been until now versus what another option might be. I take my sample. I get a sample mean of 16.5. Did that tell me to reject the null hypothesis? Did it go down? Well, my sample certainly did, but it's just a sample. Maybe your sample went up. How can I infer from my sample whether or not it is low enough to reject the null hypothesis? Well, you find the p-value. That's right. You see, how likely is it that I got what I got without... Yes, you can do it that way for sure. But one way or another, you find the p-value. So in this case, let's actually do it just for, shits and giggles. So what do we have? We have 10 mice. That's my n. We have the sample mean. But there's not enough information. What are we missing? Well, I had an initial thought for a second of actually computing the p-value. Good, excellent. I had initial thought for a second of actually computing the p-value, but they don't give me enough information because I'm missing sigma. All right, without sigma, I can't do much. And the question didn't ask me to, so I didn't need sigma to answer the question. It just was a follow-up question. Like, hey, you know what? Let's for fun. Let's see what we get. But without knowing sigma, there's no way of knowing the answer. You okay?
Yeah.
Okay.
Everything you need?
Yeah, I'm just teaching. I forgot to ask what's on the menu today. Dad, what are we eating tonight? Surprise me.
Okay.
Okay.
When do you want it?
I'll take it now. They want to know what I'm eating. I want to know what I'm eating.
Tell them petit de foie gras.
English, man. English. Okay.
Okay.
Let's see what else we got.
Hold on.
So we can get more of this. So those are already exercises, but let's do an exercise too. Exercises are good. It's not just multiple choice, but we actually get to think a little bit. Well, let's do number 30. So let's go ahead and take a minute and read number 30. Okay, so successful hotel managers must have personality characteristics traditionally stereotyped as feminine, such as compassionate, as well as those traditionally stereotyped as masculine, such as forceful. The BEM sex role inventory is a personality test that gives separate ratings for female and male stereotypes based on a scale of 1 to 7. Although the BSRI was developed at a time when these stereotypes were more pronounced, it is still widely used to assess personality types. Unfortunately, the ratings are often referred to as femininity and masculinity scores, which, is very archaic. A sample of 148, I stopped there. Why do I stop there? Why do I stop as soon as I read a sample of 148?
Because you want the actual mean and not the sample mean.
No, not exactly. I stop at 148 because I recognize that's an important thing to have in this problem. That's my N. I have all these formulas that I'm going to be using, and I want to spot what I need as I read through the problem. Does that make more sense? Okay. So a sample of 148 male general managers of 3 and 4-star hotels had mean BSRI feminine score X bar equals 5.29. That's always great because they don't tell me, I don't have to figure out, oh, that's my X bar. They told me that it was X bar, which was fantastic. The mean score for the general male population is mu equals 5.19. Do hotel managers on the average differ statistically significantly in femininity scores from men in general? Assume that the standard deviation of scores in the population of all male hotel managers is the same as a sigma equals 0.78 for the adult male population. A, state the null and alternative hypotheses in terms of the mean femininity score mu for male hotel managers. What is the null hypothesis?
Is it 5.19?
Is what's 5.19?
U is equal to 5.19.
Excellent. Mu is equal to 5.19 because after all, this is the value for the entire male population. So why would we think otherwise? And what are we testing against mu equal to 5.19? What are we testing? What's our alternative?
Is it not equal to?
Yes, that's what differ means. Is it not equal to? Bigger, smaller? That's not what I'm looking for. I'm looking for differs. I am looking for not equal to. So that is my that is my null and my alternative hypotheses. Part B, that was part A. Part B.
Question.
Yes.
Would this be a two-sided?
Yes, it would.
Okay.
Not equal to means bigger than or smaller than, either way, both sides. B, find the test statistic. Well, what's the formula for the test statistic? I believe we did it a few minutes ago.
X bar minus the mu given, or how do you say the U thingy with the O?
Mu naught, N-O-U-G-H-T, mu naught.
Okay. And then U divided by the square root of n.
sigma divided by the square root of n. That is the formula for your test statistic. What is X bar in this example? .29. They literally tell me that. What is mu naught in this example? .19, because I gave you that. That's the null hypothesis. What is sigma in this example? .78. They gave me that. And what is n in this example? 148. Mariah's on fire. So no need for crunch it because that can be done on a good old-fashioned calculator. So I get a test statistic of 1.56. I approve. I have 2 pastrami sandwiches and a pear because, you know, got to eat healthy. So I get 1.56 as my test statistic. Yes, pastrami. What's wrong with pastrami? Pastrami is good. So the question, well, you got good taste. Now, part C. What is my p-value? What is my p-value? How do I compute that without crunching? Google, pretty much. But let's at least understand it. I have my normal curve. I have 0 right in the center. Yeah, there should be. My value is 1.56, which is off here to the side. And if I said shade the p-value, what would you shade in on this picture? What would you shade on this picture to represent the p-value?
Would it be all points to the right of the z-score?
You mean this?
Yes.
Close, but no cigar.
As well as the other side, the other
As
half of
well
the
as the other side. It's a 2-sided test, which means if I want to be further away from 0 than 1.56, it's not just to the right of 1.56, it's also to the left of negative 1.56. So what is the likelihood of falling in that region? Well, we can certainly do a Google calculator. So my raw score was 1.56 with a 0.1. Oh, no, that's not what I want. The p-value is the probability being past your z-score in terms of further from 0. But if it's two-sided, then it's both sides past your value. So if you got 1.56, then to be further from 0 means past 1.56 or past negative 1.56. Where if it's one-sided, it's just past 1.56. So in our case, I don't think this is the one I want. Let's try this one. Here we go. So we want, there we go. We want being past 1.56 or less than negative 1.56. I don't think I can have that there. Okay, I guess what we want is, z is 1.56, and we want to calculate this last box down here. So we get 0.11876, which you can see from the looks of it is the shading on the right and the shading on the left. So our answer is 0.11876. So our p-value, hold on, p-value is 0.11876. Now, I don't really recall, but what was our alpha? Did they tell us an alpha to use? That's sigma. Good joke. They do not tell me an alpha, which means, what do I use as my alpha in the absence of them telling me an alpha? %. So our answer is bigger than 5%. So what do we conclude about this test? Do we reject the null hypothesis, or do we not reject the null hypothesis? We do not reject the null hypothesis. In other words, there is not enough evidence to support the claim that hotel managers are any different than regular men in this regard. The data does not support that. If you really feel that they are different, take a bigger sample. The bigger the sample, if you look at this formula here, the bigger the sample, then the denominator of the denominator gets larger. If the denominator of the denominator gets larger, what happens to z overall? If you have a fraction and you have a denominator in the denominator, what happens to the fraction as a whole? Nobody? How's your algebra skills? You flip it and bring it up? Bad. So what happens? Oh, I finished today. What happens? It gets larger. Because it gets larger, then a bigger sample leads to a larger z-score. However, at the same time, the bigger the sample, the closer that this number is to this number, which means the difference gets closer to 0. So that makes z get smaller. So you have these two competing factors, one trying to make z bigger and one trying to make z smaller. Impossible to predict in advance which way it's going to go, which is why you just take your data. You don't go into a statistical test biased towards one answer or the other. As a statistician, you come in saying, the data will give me the answer. Any questions on that one? Let's do 37. So, what is bad, or at least how do you know that the p-value given is incorrect? Anyone? What's the p-value in question 37? What do they tell you it is? No, z is 1.33, not p. What's the p-value? Anyone? Greater than 1. That's all we know about it. It's greater than 1. Why is that an issue? Okay, so a p-value is a probability. It's the likelihood of getting a certain result. That would mean that there's a bigger or a greater than 100% chance of getting the result that you got. How can there be a greater than 100% chance of something occurring? Right? Impossible. The report is wrong. How do I compute the p-value for a z statistic of 1.33? Google what is, or crunch it. Let's go back here. Z of 1.33. By the way, is this one-sided, two-sided? What are we dealing with in this problem? Where'd it go? Where did it go? 37. How do I know it's one-sided? We're testing whether it's more likely. So that would be the second one. That gives me a z-score of a p-value of 0.09. Why is the probability over 100% impossible? If something will definitely occur, that's 100%, right? Correct? So how can you have something that's more than 100%? Yes, no, maybe so. So what is the p-value? Oh, that's the wrong one. Don't look at that. Uh-oh, the wrong one. That sucks. I wanted to go into, where did it go? Oh, there it is. So what is the, what's the p-value? .09. So .0918. Make sense? Yes, no, maybe so. Let's try 41. That looks like fun. Go ahead and read 41, please. Let's clear this out. Go ahead and write out on your own paper what you think the null and alternative hypotheses are. That way, when you see them, you'll know whether or not you had it correct versus, oh, yeah, I would have written that down. The null hypothesis, you can write it out in words, but at the end of the day, it's always saying that something has a certain value, especially in this class. And at this point, the only ones that we've done anything with are means, nothing else. So whoever thinks they know what the null hypothesis is, mu is equal to what? No. Where do you get 0.103 from, by the way? Where did that come from? Ah, so you're using your sample, but the sample never plays a role in the hypotheses. The sample comes after the hypotheses. So nothing from the sample can ever appear in these two guys. It's all in this paragraph. Of course, not n, that's just 16. So it's not that number. What are we testing? Does iGrease work? We're testing whether or not there is a difference with iGrease minus without iGrease. If there's no difference, then what should this be equal to? 0. The null hypothesis is that it's 0. On the other hand, if iGrease does work, then the sensitivity with iGrease should be, I guess, greater than sensitivity without iGrease, right? And therefore, mu should be what? Greater than 0. That's the null and alternative hypotheses. So we take an actual sample. And we compute our sample mean. It's important to know what your sigma is. Can't do much without sigma. So let's see if they give it to us. Oh, they do. Look at that. How exciting. Sigma is 0.22. Without that, can't do much. And it's normal. Need that. It's an SRS. Need that. What was our X bar? Someone had written that a few minutes ago. What was X bar? Someone had added them up and divided. What was the number that we got? 0.0103 or something? 0.1013. And the question is this a statistically significant result? Is it far enough away from 0 given my sigma and n? So I will reject or not reject the null hypothesis. In the interest of time, I'm going to use Crunch It. Sorry, because Crunch It just does it quickly. When I look at Crunch It, it already has all my data here. So I go directly to statistics, Z, one sample. Hypothesis test. What's the mean under the null hypothesis? Zero. Is it two-sided or one-sided? Is it less than or greater than? What's my standard deviation? Do I want to use my summary, or I just list the number and the sample mean, or do I want it to actually compute it for me by just giving it the column that I want my data to be in? Well, even though I computed this, perhaps it's rounding, so let's use the actual diff column, diff, and then we will go ahead and compute it, calculate. So first it does give me 0.1013, which is great to see. That means we did our math correct. And more importantly, it gives me my p-value. What's my p-value? %. So let's take a look. Do they give me in this problem? Do they give me an alpha? They do not give me an alpha. So when they do not give you an alpha, what do we use for our alpha? 5%. Is my p-value greater than or less than alpha? Therefore, is the result statistically significant? Yes, it is. Remember, less than alpha means it's a statistically significant result. And therefore, my conclusion is what? What do I do with a statistically significant result?
You have to reject it.
You reject the null hypothesis. So let's see what they say. We test H naught mu equals 0 versus HA. They use HA, I use H1, different notation, same thing. Mu greater than 0. We test the hypothesis, X bar negative point. Negative 0.10125. Well, that's not what we got. Is it? We got positive, right? Oh, so how nice. Oh, but look at that. It's a typo you can see because in the next step, they don't have a negative here. They just have positive. So this negative sign is a mistake. It should be positive. They get a Z statistic of 1.84, which is what we got here. And a p-value of 3%. Conclude. The sample gives significant evidence at alpha equals 0.05 that now, so the one thing you want to throw in is you want to make sure at the end of the problem, when you actually do talk about your conclusion, that you do so in the context of the problem. The problem is about eye grease affecting sensitivity. So you don't just answer, oh, we reject the null hypothesis. You get specific to the problem. We reject the fact that eye grease does not affect sensitivity, that there's no difference, in favor of eye grease increasing sensitivity. So you want to write out a sentence in the context of the problem and not keep it purely mathematical. Does that make sense? I hope it makes more sense. This is only the intro. Sorry, you said something?
Yeah, I just have a quick question because I think I was confused this entire lecture.
Cool.
So if if it's less than alpha, you accept it or reject it? I'm
Reject it.
confused. Reject it. And if it's greater, you accept it.
That's right.
Okay, cool. Thank you.
You're welcome. So how does 3% go into the problem? Because 3% is what we compare to our alpha. If our p-value is less than alpha, you reject. If the p-value is not, you do not reject. This p-value is, so you reject. That's the only place. All the math that leads to 3% is just to compare it to my alpha. If we reject the eye grease, no. Remember, the null hypothesis is that there's no difference. That's what we're rejecting. We're rejecting the fact that there's no difference. in favor of there is a difference, but more specifically that it's better, that it's gone up. So you'll see athletes do that. They'll put the eye grease there. And apparently, in ways that I don't necessarily understand, no, not 3% better. The 3% is not how much better it is. The 3% is how likely it is to get what we got. You just take that and you compare it to your alpha. And then you either reject or don't reject. That's it. You don't use that number as part of your conclusion. It's not 3% better or anything to do with that. 3% is less than alpha, done with the numbers, reject the null hypothesis. That's it. The null hypothesis says there's no difference. The alternative says with eye grease, it's better. We're rejecting the null hypothesis. We say it's better. Not how much better. I don't know. I don't care. That's not what the 3% is. The 3% is solely only on the likelihood of something occurring. Okay, so that's it for chapter 17. I deliberately did not want to move on to